Alright guys, good morning. So I'll continue with the things I was doing at last time, which was the change of form. Power series expansion, right? So again, what we say yesterday, we say, well, suppose that you have a function defined in a region that is analytic. And in a region D, and let and take a this that is inside the center alpha and radius r. So what we say is that we can pick another disk, right? Or a smaller radius, say radius rho. And assume that you have a little a that actually belongs to the disk, the center alpha, but now radius rho. So rho is the radius a little smaller than the radius of the disk that is contained in the region. But then for this value of a, you can actually write down the value of the function as 1 over 2 pi I integral over 0 of f of z over z minus a into z, right? Where 0 is the curve. It's just the boundary of the disk of radius r, of radius rho. So 0 is the curve with parametric function. Alpha plus rho e to the I theta with theta with 0 to 5. So that was the Cauchy integral formula in general. You don't need the function to be entire, just the function to be analytic in that region. And take a this inside there, then you can find out a disk that contains A, and the value of A can be expressed as an integral. Now that was enough to conclude, right, that F has a power series expansion. Around alpha. Expansion into this. How we did that? Well, very easy, right? So you have, you look at this this piece, right? 1 over z minus a, and what you do is you expand that as geometric series, right? So this is what we did. So let me recall that computation very quickly. So with this, look, we take f of z over z minus a, right? Integral over 0. 1 over 2 pi I. You can see and write it as 1 over 2 pi I integral over 0 of f of z over z minus alpha minus a minus alpha. Alright? This alpha is the center of the disk, and then this computation is very important, so it's good to keep in your mind that you factor the z minus alpha factor. You factor z minus alpha here, and you get 1 over 1 minus a minus alpha over z minus alpha. And then you notice, right, that what is the modulus, right? So you take a z that is actually on the curve 0, right? Then what is the modulus of a minus alpha over z minus alpha? Well, z minus alpha is on the circle 0, right? That means 0 is what? Is the boundary of the disk with center alpha and radius rho. So if this is on the boundary, then the distance to alpha is exactly rho, right? So this distance here is exactly rho, right? The absolute value of z minus alpha. And now what happens? Oh, well, the A that you chose, right, is in the disk with center alpha and radius rho. So the distance from alpha is less than rho. So this is less than rho over rho. So that's the key part here, that the absolute value of this complex number is less than 1, and then you know that you can write 1 over 1 minus a minus alpha over z minus alpha as a geometric series. That's the key thing. That's why it's very important to choose this inside the region. And what the computation is exact sense we did, right? Then you write down f of a, right? Which was that integral as 1 over 2 pi I integral over 0, and then you take f of z over z minus alpha, and then you expand that as a geometric series. So it gives you the sum from n equal to 0 to infinity of a minus alpha over z minus alpha to the power n, and of course you are integrating everything with respect to z. And now the key thing here was that you were able to interchange the integral with the sum, right? And then you can put everything inside the sum. So from n equal to 0 to infinity of what? Of 1 over 2 pi I, right? If I put that in, and I integrate term by term, but term by term this is f of z, integral over 0 of what? Of z minus alpha, and this has 1 power and for each one of these n's, power m plus 1, and then you have the a minus alpha to the power n, dz, right? And then you figure that, well, this term here doesn't really have the variable z, so it's constant, and you can take it out from the integral, and that becomes the sum from n equal to 0 after infinity of 1 over 2 pi I integral over 0 of f of z over z minus alpha to the power n plus 1 dz, all this number, right, times a minus alpha to the power. So if I call that number Cn, right, that becomes the sum from n equal to 0 to infinity of some constant, right, because this is just a number that you compute, times a minus alpha. It's like the same computation as before. So you have a function that is analytic, right, on a region D. You can take a disk, right, that is inside that region. And inside that, and on that disk, you have Cauchy integral formula. And Cauchy integral formula also tells you that you can write, you can get the values of the function, right, as an infinite sum. And which was, that A was what? Yeah, A was everything, right, that was in that disk. Because no matter which thing you take in that disk, you can always choose some piece of radius rho, right, that encapsulates, that encloses that number A, that complex number A. That means that this convergence, right, is for every A that is in the disk. And that was just any disk that was in the region D. So if you take the largest disk that is in the region D, right, and you will have convergence. You will have so that is the I want to just explore now some consequences of this and maybe solve some of the problems in the book. Some of the ones that I suggested, because I realized they are not as easy. So maybe I should give some hints. But the key thing is here is the following. So it's this uniqueness of coefficients of a power series. So I mentioned before that if you have a series, right, a power series, converges to some function f of z, right? In some data with center A and radius r. Then the derivative of that series, right? That is taking derivative term by term, which is n cn z minus a to the n minus 1, right? And the power here is 7.1. That thing actually converges, right, to the derivative of this function, right, for all z in the same disk. So if you have a power series converging some disk to some function, then actually that function has a derivative, right? And that derivative also has a power series expansion, and the power series expansion is just taking derivative, term by term. But then I can do the same now with f prime, right? Because f prime has power series expansion that converges in that case. Then I can take the derivative again, right? And then the second derivative also converges in the same disk. And I can take the third derivative, right? And I can take any derivatives that I want. So if you have a function that has a power series expansion in this, that function has derivatives of all orders. So that's a consequence of this. So a corollary is that if f is analytic, on a region D, then f is infinitely differentiable. How you do that? Well, very easy, right? So you take any point of D, you have to prove that f has derivatives of all orders at every point of D. So then you take a point of D, and because D is open, there is a small disk around that point. Right? So in that small disk, you have Cauchy integral formula, and then you can write that as a power series. Once you write this as a power series, you can take derivatives, right, of all orders. So if a function is analytic, then it's infinitely differentiable in that region. Moreover, that also tells you what the coefficients Cn have to be, right? Right? If f of z, and let me write this in a long way, right? So if you write this as C0 plus C1, C minus A plus C2, C minus A squared, plus, right? So I'm just writing it long way the series. Then the derivative, right, is what? Well, it's C1 plus 2C2, C minus A plus 3C3, C minus A squared, blah, blah, blah. Maybe the second derivative can also compute it, right? Let's do step a bit. So the constant goes away, you get 2C2, and then you get the derivative of this one, which is 2 times 3 times C3, C minus A plus, the next time we'll have what? We'll have a 4, right? And then the next derivative will give me a 3, so you have 3 times 4, right? C minus A squared plus blah, blah, blah. The curious thing here is what happens if I take those values of f, f prime, and f double prime, and I compute it at a very specific value. So what happens if I plug in A there? So what is f of A? Well, if you replace z by A, right, all of those terms after C0 are 0. And the only thing that stays is C0. Right? How about if you take the derivative of f of a? Right? If you take the derivative of f of a, then all these terms they vanish, and you can only see one. How about if you take the second derivative of a? Well, if you take second derivative of a, all these terms they vanish, and the only thing that you get is 2c2, right? Oh, but then you can also say, what happens if I take the third derivative of a? Even if I then write it down, right? The third derivative, right, will get rid of that one, and will give me just this number, right? This number times c3, and all the others will vanish. What do you think happens if I take the fourth derivative? You take the other one has a 4, right? So 4 times 3. 4 times 3 times 2, right? And if you compute the n derivative, right? You should get what? N factorial, right? N factorial. And C4. And then that says, right, that actually those coefficients, but these coefficients are not so weird, right? The coefficients actually compute the values of the derivative at a up to a factor n factorial. Cool. So if you have a power series expansion, then the coefficients are actually, arbitrary. The coefficients are actually the values of the derivatives of the function, right? At that point where the expansion is. Now look at this. So you have an analytic function, right? It has this power series expansion. So that tells me that this number Cn has to be what? The n derivative of the function over n factorial. Oh, but on the other hand, I know those coefficients are given by these intervals, right? So that gives me a formula for the derivatives of the function as an interval. Some type of Cauchy integral formula. Is that right? So just compare there coefficient Cn with those coefficients Cn. So let me write that down. And you take an analytic function. If f is analytic on this, right? Central from radius r, then you can write down f of a, right? As the sum from n equal to 0 to infinity of what a minus alpha to the power n times this coefficient Cn, where Cn is given as 1 over 2 pi I. The integral over some, this that contains the value n, right? The boundaries of those is of the values of the function over z minus that was z minus alpha, right? To the n plus 1. Easy. But now if Cn is given by the derivatives, then that value, right, it's equal to the n derivative of the function at where? Oh, wherever the expansion is, right? At alpha. And that gives you a formula for the derivatives, right? So the n derivative of f at alpha is n factorial over 2 pi I integral over 0 of f of z over z minus alpha to the n plus 1. Why is that important? Well, you can solve a lot of cool problems with this. So then, let me give you some examples. exercise 5.7. I don't know if anyone has thought about it, but maybe this is it's good to see one so you see what's going on. Says, suppose that f is entire and that the absolute value of f of z is bounded not by a constant, because if you were bounded by a constant, then f will be constant, right? Because that's liable zero. But says a little bit weaker, something weaker says, how about if the absolute value of f of z is less than a constant plus another constant times absolute value of z to the 3 times. Because well, if that happens, they're going to ask you to prove that f is a linear polynomial. So not an arbitrary entire function will satisfy that the modulus of f of z is bounded by something like that. So if that happens, the function has to be a polynomial of degree 1. There is no other choice. Now, what is the particular thing about polynomials of degree 1? That if you take the second derivative, you get what? 0, right? The first derivative of polynomial of degree 1, you get a constant. Second derivative is 0. Now, if the second derivative of a function is 0, right, that means that the first derivative is constant. Is that right? Because we proved that, right? The derivative of function 0, the first derivative is constant. And then, what is an antiderivative for the constant, right? It has to be a constant times z plus another constant. So it's if and only if, right? So a function is a polynomial degree 1 if and only if the second derivative, right, is 0 everywhere. So what we have to prove is that the second derivative is 0. Now, that seems something very hard to prove, right? Just from the information on f, right? Because you would like to prove the second derivative 0, and you have information only about f. So if you try to do this just by hand, right, you would have to write the second derivative as a limit, right? Because the second derivative, how the second derivative relates to f, right? By taking this limit twice. So we have to write this double limit, right, in terms of f, in order to be able to use the hypothesis. Right? So that's something that seems, I don't know, the rate of success seems very, very small. But now we have this formula that tells me that the derivative of the function can be actually computed in terms of f, right? So that is an advantage, right? The derivative of the function is computed in terms of the values of the function, but after some integration. So what I will try to attempt to do here and show you how to do is show that the second derivative is 0 by using this formula mixed with the hypothesis. So how will that go? So by the Cauchy integral formula, for derivatives, what is the second derivative of the function at z? Let me write z. So the second derivative function at, or maybe at a, we went to do a. The second derivative function at a is n factorial, in this case is 2, over 2 pi I, integral over some 0, right? I don't know what rho is. Rho can be actually anything, right? Because the function is entire. And the function is entire means I can take any disk of any radius, right? And the function will be analytic there. And that was the only requirement for rho. So I can actually take any disk, right? Because the function is entire. So that's a good thing to know, that this rho is arbitrary. We will actually use it in a moment, but for now, this, I'm just making the remark here that this rho is arbitrary. So you get that thing times f of z, right? Over z minus a, right? Because it's at a. power n plus 1 is the second derivative is to the power 3. All right. And how, if I would like to prove that that thing is actually 0. Now, what is the easiest way to prove that a complex number is 0? Maybe you have seen me do this thing several times. How do we actually prove that a complex number is 0? Take its modules, right? And prove the modulus is 0. So, right? If the modulus is 0, then there is no chance for the complex number but to be 0, right? So, and that is a good idea because the hypothesis that is given to me is in terms of the absolute value, right? So what happens, if the R is true, then I can take absolute value of this, right? That would give me that. And well, by things that we have proven here, this is less or equal to 1 over pi integral over 0, right? Of the modulus of f of z over the modulus of c minus a to the power 3 times the z. All right. Now, what is 0? So recall that 0 is the boundary of the disk, right? Center at what? Center at the value where I want to compute derivative, right? So center at A, right? And radius rho, right? Then, if you take, right, a z that belongs to 0, then what will be the distance from z to a? So 0 is the boundary of the disk, right, with center at a and radius rho. So you take anything on that boundary, what is the distance to a? Is rho, right? So this z minus a is actually rho. Right? The picture is very different. I'm taking the a in the middle, right? This is 0. This is a distance center rho, and 0 is just this curve, right? That goes around. And when I'm integrating, right, because it's this z and z is on the circle 0, right? So z is any value here, and the distance from here to here is exactly rho. Right, so absolute value of z minus a is actually rho, so that is very helpful because I have then that the second derivative of a, absolute value, is less or equal than 1 over pi integral over 0, right? Of the absolute value of f of z, which is less or equal than a plus, right, b times absolute value of z to the 3 halves all over rho cubed. And of course, now absolute value of z, I don't know how to control that yet. So I have to do something because absolute value of z is not really related to rho right away. Is that right? That is just absolute value of z, and z can be anything on this equals 0. So I cannot really know what that thing is. However, right? If you have absolute value of z, that is absolute value of z minus a plus a, and that is less or equal to absolute value of z minus a plus the absolute value of a. So right, just by triangular inequality. And now what is the distance between z and a? Well, I just say, right? That is rho. So that thing is rho plus the absolute value of a. And then we combine all these things. right? So you take the absolute value of the second derivative of f at a, that is less or equal, right, than 1 over pi integral over 0 of a plus, the absolute value of z, right, is less or equal than rho plus a. So plus rho plus a, rho plus the absolute value of a to the 3 halves, right, all over rho cubed dz. And the matter here is that there is no z here anymore. So because there is no z here anymore, I can take it out from the integral, right? So that becomes 1 over pi times a plus, was there a b? There was a b. I didn't write the b. A plus b times rho plus absolute value of a, all to the 3 halves, right, over rho cubed, times the integral over 0 of this absolute value of this. Now this integral here computes what? Computes the length of 0. And what is the length of 0? It's a circular radius rho, right? It's 2 pi times the radius, right? Which is rho. So that is 2 pi times rho. 1 over pi times a plus b, rho plus absolute value of a to the 3 halves over rho cubed times 2 pi. Well, that doesn't seem like 0, right? It's not a 0 value, so you say, well, so did I do anything wrong? I don't know what else to do. And then, you remember that I told you that the radius can be as large as you want, because the function is entire, right? And you only require to take a disk where the function is analytic, right? But that disk can be as large as you want. That means that you are able to take the limit as rho goes to infinity here, right? But what happens? What is the power of rho on the top here? 3 halves, right? So rho is of order 3 halves on top. On the bottom, right, one of these rows they cancel, rho has power 2. So the bottom has more weight in rho. So when you take limit as rho goes to infinity, that part goes to